Hi, in this video, I'm going to introduce the second equivalent circuit theorem over here. It's called Norton's theorem. So the description is any linear circuit can be converted as a following equivalent circuit. Just keep this in mind. So the Thevenin's theorem and also the Norton theorem, the purpose of these kind of things are just to simplify the circuit. Okay, the equivalent circuit we are going to convert the original one to, will be perform the same function to the load. So the Norton's equivalent circuit looks like this. It's a current source and a resistor, which is a Norton's equivalent resistor. It's called Rn, and here's a load, it's RL. It's provided by the user, so it's not being changed. This is Rn, this is In. And keep in mind, Rn equals to RTH, which is what you learned in the last lecture for Thevenin's theorem. And let's look at an example. If you have a circuit looks like this, there's a voltage source over here. That's 8 volts. I just mixed that. And this is 8 ohms. This is 16 ohms. And you also have a RL over here. And this is 2 amp current source. So what's the procedure to convert a regular linear circuit like this into its Norton's equivalent? So let's find out Rn first, because Rn is the same as RTH. So we are not going to repeat it in detail, but I'm going to just show you the procedure of it. Okay, so for Rn, step 1, remove what? Remove RL. Step 2, what's step 2? Disconnect current sources and short voltage sources in the circuit. And step 3, just calculate or get Rn. So let's take a look how I'm going to do that for this circuit. Definitely remove Rn, disconnect this guy, short this guy. So eventually you only have one resistor here and one resistor here, right? Because if you compare these two circuits, it used to have a current source over here, but it's being removed. So there's nothing over there anymore. And this guy, there used to have a voltage source over here, but because it's being shorted, so it becomes a wire afterwards. So I have an 8 ohms resistor and 16 ohms resistor over here, and RL is removed. So it's just thinking like you are the person looking backwards. So what's the equivalent resistance? It's pretty simple. So Rn equals to 16 ohms plus 8 ohms, which is 24 ohms. All right. So what about In? Because the equivalent circuit requires both Rn and In. So In is being calculated slightly differently if you compare to the Thevenin's theorem. So for In, how to do that? The procedure, okay. Step 1, you draw a wire from the output terminal to short the load resistor. And step 2, the current flows through that wire. Flows through that wire is IN. That means if you draw a current, if you draw a wire here, so this will be IN. So definitely keep the current source and voltage source in there because they are both contributing current to this guy. You can imagine that if you draw a wire here, this guy will be shorted. You don't have to remove it because it's being shorted, so no current is going to flow through this guy. So you just need to draw a circuit like eventually this one will be converted into something like this. All right, and you just need to find out what's the current in this wire, and that will be IN. Okay, how do we find out the current over here? Of course, you can use a mesh current method, no problem. Let's do it, see if that works. You can see that I2 is a mesh current in this mesh. It's exactly IN. So if you can find out I2, you don't need to know, I1 is given. I mean, it doesn't matter if you know it or not. It's given, it's 2 amps because I1 is going up. It's the same current as this mesh current. You just need to calculate I2, which is IN. So let's do it. First of all, we know I1, so we don't need to list the current equation over here because it's given. The only reason you want to list that equation is because you don't know it, you want to calculate it, but now it's given, so we can ignore that. So only for this one, if we start from here, traveling from here, we're having minus 8 volts plus, what is this? It's A times I2 minus I1, and plus 16 times I2 equals to 0. And because I1 is given, so we just list I1 is 2 amps. You just substitute I1 in here using 2, and you are getting minus A plus AI2 minus AI1. AI1 will be A times 2 will be 16, plus 16I2 equals to 0. So you can calculate I2 from this equation. So what is I2? This is 24, move to the right side, it's going to be plus 24. So it's actually 24 I2 equals to 24. I2 will be 1 amp, and which is exactly IN. All right. So now you have both IN and RN, and you can easily draw the Norton's equivalent circuit. So you can directly say, so the Norton's equivalent circuit is, keep in mind, the resistor is here in parallel with the current source instead of over here in a Thevenin's equivalent circuit. Okay, and this is RL, and this is RN equals to what? RN equals to 24 ohms. So it's solved, and IN equals to 1 amp. And that's it. So that's a Norton's equivalent circuit of the original linear circuit. So you can see the circuit has been significantly simplified using this method. And also, you can convert it into Thevenin's equivalent circuit from here to, the counterpart, which is a Thevenin's equivalent as well. It's just like 2 different ways to convert it into either a voltage-driven equivalent circuit or a current-driven equivalent circuit. Doesn't matter. Depends on the need. Okay. All right. So in the next lecture, I'm going to cover superposition, which is also pretty important. We'll see you in the next lecture.